Hello everyone, this is Dr. Young, and in this video we're going to continue to talk about quantum mechanics, or our path to quantum mechanics. And we're going to continue to talk about the Bohr model and then the expansions and the things that were built on that, like the idea of energy being quantized and the fact that electrons have wave-like properties. So now again, in this video here, what we're going to see is we're talking about this idea of quantized energy levels, relating it to the Bohr model and talking about electrons as being standing waves or having the properties of having standing waves. So remember that Max Planck proposed these quantized energy levels. He was a pianist. He kind of that made sense to him that you could be at one key versus the other, but one key versus another key, but there's no key in between. He thought that energy levels might be like that too, that you're at one energy level or you're at a different energy level. There was not an in between, or in other words, that those energy levels are quantized. And he had this equation, right? This is the Plonk equation, that energy equals Planck's constant times the speed of light divided by the wavelength of that photon of light. And in the previous video, I showed you how to calculate the energy of a photon, but you could go the other way around, right? You could ask yourself, what's the wavelength of a photon with an energy of like 4.90 times 10 to the negative 19 joules? And you do the similar sort of math, right? So you start off with your equation, E equals hc divided by lambda. If you rearrange that, because we're going to solve for the wavelength here, then you just get hc over E. And if you plug in all your stuff, so remember that Planck's constant is 6.626 times 10 to the negative 34 joule seconds. Speed of light, we're saying, is approximately 3.00 times 10 to the 8th meters per second. Put that over the energy that we have, which is 4.90 times 10 to the negative 19th joules. And you get that we have 4.06, let's say, times 10 to the negative 4th meters. Or in other words, 406 nanometers. That'd be the wavelength of light that has 4.90 times 10 to the negative 19 joules, right? That one photon. And remember that this is really important because that helps to inform what are the energy differences between different levels, right? We'll talk about Bohr model here again in a second, but when an electron jumps from one orbital to another orbital and it absorbs a certain wavelength of light, that wavelength of light corresponds to a certain energy level. And so that allows us to figure out what the difference is in the energies between those energy levels. So like the Bohr model, right? Remember that the Bohr model built off of the Rutherford idea where you had a bunch of like protons and neutrons in a nucleus. Let's just say it has like this. Bohr's addition to this, to what Rutherford was doing, was saying, okay, yeah, we know that electrons are not in the nucleus, that there's sort of this electron area around the nucleus. But remember that Bohr said, oh, you know what? We have orbitals. That he thought that the atom looked like a planet where you'd have these electrons. So these little green dots are going to be my electrons, abbreviated E with a negative sign. That you had all these electrons, and as these electrons were flying around, right, that they're orbiting the nucleus, right? So you had the nucleus. You had these, what he called orbitals. And then, like I said, in the green, those are the electrons. So the electrons would orbit the nucleus in their orbitals. And he was saying that, okay, well now if you have a photon come in, what can happen is a photon can come in. This would be a photon. Sometimes we abbreviate photons as an h nu to kind of, it's just another abbreviation for photon, it's h nu. And he's saying that when you hit an atom, what you can do is you can promote, right, that electron. You can excite that electron up into a higher energy orbital, right? So you have this excitation. So now this electron was promoted or excited into a higher energy orbital. Into a higher energy orbital. And the higher energy orbitals are the ones that move away from the nucleus, right? You're getting further away from the positive charges in the nucleus. Electrons are negative. they're attracted to each other, so as you move further away, you increase the energy. And he's saying that when you do that, that photon gets absorbed. And that absorption is why we see these gaps in the electromagnetic spectrum. You can't see the red marker there. Why you can't see the gap, or sorry, that's why you see gaps in this spectrum, is because a given element absorbs light when it's promoting electrons. When light of just the right frequency hits it, then you can absorb that. And like I was saying on the previous slide, right, the idea here is that this energy level, this delta E, right, we can figure out what wavelength of light that is. We can calculate that, right, which what I did is what I did on the previous slide there. Now, while Bohr thought that the electrons were particles moving around, right? They're just like planets, like they're just particles like planets moving around the nucleus. A French scientist, Louis de Broglie, I have a terrible French accent, but it's de Broglie. He thought that, well, you know what? If light has particle properties and wave properties, maybe an electron does too. Maybe an electron also has particle properties and wave properties, because they're both really, really small. They're both weird. So what would that mean? And so he combined Einstein's famous E equals mc squared equation, right, where the energy equals the mass times the speed of light squared, with Planck's equation, where energy equals Planck's constant, speed of light divided by the wavelength. He put them together to get this new one, right? Where this is basically saying that the wavelength of an object, right? So this is your lambda, this is your wavelength. Your wavelength of an object, and this would be in meters, can be calculated by Planck's constant, which is, right, 6.626 times 10 to the negative 34 joule seconds. This m here is actually a length. This is in meters. This is the size of the thing. And then this is v for velocity, right, or speed. And that's in meters per second. Oh, I'm sorry. That's meters per second. I was just joking. This m is not meters. This is a confusing part. See, I just confused myself. This is not meters. This is mass. This m is mass. This m is not meters. So that's going to be in mass and in kilograms. And you just have to, and we're not going to go crazy into the math with this stuff, so don't worry too much about this. But in order to do this, what you have to do is you have to convert these joules right here, right, the joules from your Planck's constant. You need to convert that to these joules, right? That the kilograms times the mass, or meters per second squared. So if you convert that, you can actually calculate what the wavelength is of really any object at a given speed. And so what he did was, de Broglie calculated that electrons are so small, and the speed at which they move, they're so small that like 20% of its size, that its wavelength is 20% of its size, right? That's like a human being, right? If you're just walking around, that's like you having a wavelength. You are moving like a wave at about like a foot and a half, right, of your total size, which is like so weird to even think about people being kind of like waves, where we can travel, we could have standing waves, or we could have constructive or destructive interference. But that's very significant, that 20%, right, its wavelength is 20% of the size of the electron. So we thought, okay, you know what? That means that they do have wave-like properties. And so what are the consequences of that? And to give you an idea, right, before we talk about the consequences, to give you an idea, you can calculate this for a human, right? You can use the same equation, calculate it for a human. So I picked, well, what if someone weighs 70 kilograms and is walking, which is about 1.8 meters per second. It's about 4 miles an hour. If you do that, you get that a human being's wavelength is this tiny, 5.3 times 10 to the negative 23rd nanometers, or in other words, 2.7 times 10 to the negative 36% of the size of a human. That is so tiny compared to the size of a human that our wave-like properties, and we do have wave-like properties, but it's just so tiny that it's irrelevant. It doesn't make any difference, right? We work on Newtonian mechanics. Newtonian physics, not quantum mechanics, not quantum physics. It's just we don't have enough wave-like property to behave like the things at the electron scale and the photon scale do. So yes, any object can have a wavelength using de Broglie's equation here, but it's just for humans, it's irrelevant. For something as small as an electron, it's significant, 20%, versus us, it's this real tiny amount. So what are the consequences then of an electron having wave-like properties, that it moves kind of like a wave, that it is kind of like a wave? So de Broglie was saying, well, if electrons have wave-like properties and they're moving around a nucleus, right? So he's kind of still liked Bohr's idea that electrons moved around a nucleus, and it was known that there were electrons around the nucleus. But he's saying, well, if they're moving around, they got to be moving as a wave, and they got to be moving as a circular standing wave. That'd be the only way that it could be stable enough to be in existence. So the question then becomes, well, what is a standing wave? So I want to show you this PhET simulation here. So let's talk about the difference between a standing wave and a traveling wave. So I've got another PhET simulation here. If I click on this, what you're going to see is that I'm going to shoot just a single wave down a string. You just flick a string or flick a spring or something like that. And it moves up. There's a fixed point, so then it's the negative, and then it's the positive, and then it's the negative. Or another way to say it is that it's the crest, or it's a mountain, and then it's a valley, or it's a trough. So you go crest to trough. And this would be a traveling wave, right? You can clearly see it's moving. Every single bead in this string is flicking around and moving at some point. This is not a standing wave. Standing wave is when you are oscillating and you have waves that are overlapping with each other in a way that you start to form these nodes, and it looks like some parts of the wave are not moving. So let me show you that. So I'm going to go to oscillate in slow motion here. So I'm starting, right? That's a traveling wave. You can see it traveling down and all of the beads are moving, right? Notice that all of the beads in this first part are moving. And what we're going to see is something interesting happen when you get down to this vice, this fixed point, when the wave is going to start going the opposite direction and underneath. So it's moving, but then once it starts moving underneath, look at how now there start to be these fixed points that show up, right? This red bead right here, this green bead right here, this red bead right here, and in a second, this green bead is going to start forming a standing wave over here on the right-hand side, and as the wave moves over, it's making the whole thing become a standing wave. So if you noticed, right, all of these beads that are on this orange dotted line, they didn't move as this standing wave was created. Now I'm continuing to add energy in here because I'm continuing to flick it, so we're going to see it kind of grow a little bit more, but I'll show you that. But this is an example of a standing wave, right? I have parts that are going to oscillate, and I have these nodes that don't really move, right? This is a node, that's a node, that's a node. And it looks like just the string is going up and down in those spots. And again, once this wave travels down, it comes back. Now again, right, over here on the right-hand side, you can see very clearly the standing wave action of this, where I don't have parts that move, and I have other parts that move a lot. And so that's what's meant by a standing wave. It only works if you have certain, like the right amount of energies. So like, for example, if I restart this, and I have a different frequency, which, right, remember, corresponds to energy, and I'll change some amplitudes, and who knows. But if I do that and I just run this, I'm not getting standing waves here, really, right? I mean, this is just going kind of crazy. Everything's moving. It's not nearly as nice as I had it before. And so the idea is that you only get standing waves when you have just the right frequency, just the right energy, right? Which is part of this idea of energy being quantized. You need to have just the right energy, just the right frequencies in order to get these standing waves. So let me show you some more animations of what a standing wave looks like. So here's another way that we can represent these, right? I showed you that simulator, but here's just some animations of a standing wave, the lowest energy standing wave you can get, which has no nodes. You can see the whole thing just goes up and down. Here would be one node, right? Notice in the middle right here, it doesn't really move. That would be your next highest energy, the next mode that you could get. And then so on and so forth, right? This one has two nodes, one right there and right there. This one has three nodes. And so the higher energy you get, the more energy you put into it, the more nodes you can get out of a standing wave. But again, there's only certain amounts of energy that can do this, right? If you imagine doing this, and you may have done this before, if you do it with like a jump rope or a slinky and you flick it back and forth, you can try to get these standing waves yourself, but it's a little hard because if you're not exactly right, you don't get the standing wave. You just get a weird wavy mess. Now, those are linear standing waves. De Broglie proposed electrons move around in a circular standing wave, which is kind of crazy. A circular standing wave is the same idea. It's just that instead of moving in a straight line, this wave is moving in a big circle. But again, you have to have very specific frequencies and wavelengths so that the wavelength matches perfectly so that it can follow the circumference of that circle and match up with itself just right so that it can constructively interfere. So a circular standing wave is very similar to a linear one. It just moves in a circle. But it's similar in that you have to have just the right wavelength, just the right frequency of light, the right energy to have them. Right, so we have linear standing waves, we have circular standing waves. And the idea is that with these circular waves, you can't have just any energy for this electron. Because if you have just any energy, then you have a chance of when this electron takes off, and let me draw it this way, when an electron takes off, if it's not of the right energy, right, if it's not of the right wavelength, as it's going around in a circle, it's not going to match up. Right? It didn't match up here. This is a problem. Right? It does not match up. So it did not have the exact same path. I'll say it will not have the same path. It will not have the same path, which means this is a traveling wave, not a standing wave. Whereas this one over here on the left, right, if you start, the idea is that this wave, you move up and down as you're going around in a circle, but because it's just the right energy and therefore has just the right wavelength, it matches up on itself perfectly, and so it is a standing wave. It is not a traveling wave, it is a standing wave. It is just a free wave sitting there because it has just the right energy to overlap with itself perfectly. And so again, you have to have the right energy so that when you come around, let me draw an example of this. If you were to just start somewhere, I'm just going to start here on my little, let me draw it. Here's my nucleus. That's that little black dot's the nucleus in the middle. And if I start at one spot and I pick an energy level, just any old energy level I want, that's going to correspond to a wavelength. But again, the wavelengths have to match the circumference of this circle. So if I just pick one, and this is going to be a terrible drawing, but just bear with me here. Right? I am not drawing see how it's not matching up at all? I am totally, this is not a standing wave. I picked one that I didn't have the right wavelengths, and so they didn't match perfectly. But there are ways to do that, right? So here's one, here's one, here's one, here's one, where you have different number of nodes, different number of bumps here, right? You've got 3 for this one, 4, 5, 6. And the idea is that this corresponds to different energy levels, right? And so you can have an energy level of this, whoops. Let me fix this here. You can have this energy level will correspond to this one, but an energy level here, for example, right? Let's just put a number so you can kind of see it. Let's just say hypothetically, and these numbers are way too big, but let's just say this is like 10 joules, and this is 20 joules, and this is 35 joules, and this is 56 joules. The idea is that only those energies correspond to these perfect standing waves. So if I just pick something like, let's just say, oh, what about 18 joules? Then I'm going to get a disaster like this. And it's not going to be a perfect standing circular wave. And so again, this reinforces this idea that energy is quantized. It has to come in these certain discrete packets. You need to be either at 10 or 20 or 35 or 56 joules so that you have the right energies so that you can form these standing waves. So again, discrete packets, there's only certain allowable values of energy. Now, this is not what Bohr was describing, right? Bohr, again, said that, well, you got an electron, you've got these electrons and things, and they're moving around in these orbitals, right? They're moving around. They're particles, not waves. and they're moving around. And that's not what de Broglie is saying. De Broglie is saying, hey, you know what? Your electron really looks like this. Your electron is kind of has these wave-like properties. It's not just a particle moving around. So people started to kind of abandon Bohr. The other problem with Bohr's model, and Bohr's model, don't get me wrong, Bohr's model is awesome for lots and lots and lots of things. And throughout chemistry, you're going to see you'll see all chemists refer back to the Bohr model all of the time. It's really, really, really useful for just countless descriptions of how atoms behave. But one of the problems with the Bohr model is that it has these particles, right? These particles, these electrons moving around. And if you move a charged particle around, it should be emitting radiation. And no one ever was able to detect that radiation from a moving charged particle going around a nucleus like that. And so people are like, something else is going on. But in a standing wave, your electron, your charged particle, quote unquote, but we know it's not a particle, it's also a wave, it's not moving, it's standing, right? It's standing still in a standing wave. And so that kind of solved that part of the problem, is that, well, if you're going with de Broglie's idea here of this circular standing wave, the electron's not moving, you don't have a moving charged particle, you shouldn't expect to see any radiation, which in fact we don't see any radiation. So this is just more evidence that de Broglie was onto something, and that electrons have wave-like properties, which is going to inform quantum mechanics and quantum, we're going to talk about quantum numbers here in a little bit. Last thing real quick I need to talk about, Heisenberg's uncertainty principle. We're not going to make a real big deal about this and talk about Schrödinger's cat and like the Copenhagen interpretation of stuff and observation effects, and we're not really going with that. All we really need to know about Heisenberg's uncertainty principle is just saying that electrons are so small and have these weird properties that you can't really know with a high degree of precision both its location and its momentum. And that's all this equation here is really saying. It's just saying that, right, so this is the uncertainty. This is the uncertainty in position versus the uncertainty in momentum. And he was calculating that if you multiply those together, right, the amount of uncertainty in position and the uncertainty in momentum, that it has to be greater than or equal to Planck's constant divided by 4 pi. Where did that come from? We don't need to worry about that, but that's what he was saying. And so that means that they're inversely proportional, right? If they can't go over this value, if you have more certainty in its position, you have to have less certainty in its momentum, and vice versa, right? They're inversely proportional. They're on that same side of the equation here. And so he's saying that when you run an experiment, you can really only find out with a large degree of uncertainty either the momentum or the position. And to just give you one quick example of that, if you want to find an electron, since electrons are so small, you got to use gamma rays because they have really tiny wavelengths. Because you need your gamma ray to hit the electron, right? And if your wavelength is too large, you're just going to float right over the electron and you'll never see it. So you got to use gamma rays because they have tiny little wavelengths. But gamma rays are really, really high in energy. So if you do bounce off that electron, you'd be like, aha, I found the electron. Here it is. I found it in a location. I located it. But that gamma ray just beat the bejesus out of your electron, and you've transferred energy. You've probably knocked it out of the atom entirely, but you've definitely changed its position. And you knew where its position was, but now you don't know its momentum. You didn't know what its momentum was. You've totally messed with that electron. But at least now you know where it was, is the idea. So you had a real high certainty in the position, but now you know nothing about the momentum. That's kind of what the Heisenberg uncertainty principle is about. And that's all I want you to know about it. So to kind of go over this again here, right? So light is weird. It has things like interference and diffraction. The diffraction was used with atomic absorption and emission spectrum to reveal that there are these weird specific wavelengths of light that are either absorbed or emitted. So people started to propose that there were quantized energy levels, right? Bohr was like, aha, well, that makes sense if you have an electron jump from one orbital to another one. And he came up with his planetary model of the atom. But de Broglie came along and said, well, you know what? If electrons are really tiny, maybe they're wave-like too. And then that kind of threw everything, threw most of Bohr's model out the window. But solve some other problems like why you weren't seeing radiation from these quote-unquote orbiting electrons. So what we're going to talk about next are wave functions and the quantum numbers n, l, m sub l, and m sub s. That's going to be our next video, and we'll talk about electron configurations too. So now we're going to kind of put this all together and talk about our actual quantum numbers and a little bit of the math that goes into that.